Okay, so today or this week we're going to be starting to introduce material from Chapter 10. All right, so Chapter 10 in the textbook deals with radical reactions. And so we've been alluding to radical reactions throughout the course. So we've encountered a couple of reactions where we said, oh, this proceeds via radical-based mechanism. We're not going to talk about it here, but we're talking about it when we get to Chapter 10. And so at this point in time, we're finally at Chapter 10, where we are going to talk about these radical-based reactions, okay? So before we can do that, we need to talk a little bit about just some basics with respect to radicals and how they're formed. So just as a note, a radical is any species that has an unpaired electron, right? So we're going to have single electrons here and not paired electrons, which will instead be two electrons, okay? Okay, so we had talked earlier about the fact that there were two different types of bond cleavage reactions, right? So we have one type of bond cleavage reaction, which is called heterolytic bond cleavage. And in heterolytic bond cleavage, essentially you have two atoms that have a bond together. That bond is going to be cleaved in an uneven fashion. That's what hetero is trying to essentially state here, right? So for example, let's say that we had X with a single bond to Y. And in a heterolytic bond cleavage reaction, Y, let's say, is going to get all of those electrons in that bond, and X is going to get none of those electrons, and we're going to end up as a product with X with a positive formal charge and Y with an extra electron with a negative formal charge, right? So again, this is our classic heterolytic bond cleavage that we've been dealing with throughout the course, okay? Now, in heterolytic bond cleavage, we produce these charged species, which are called ions. So we have a cation, the positive charge, an anion, the negative charge. And so all of these heterolytic bond cleavage reactions, these are all dealing with these ionic mechanisms or ionic reactions, okay? Because again, they produce ions. Now, when we draw out the mechanism for these heterolytic bond cleavage reactions, this is when we use the double-headed arrow, right? The double-headed arrow is supposed to be representing the movement of two electrons. So movement of two electrons as opposed to just one, okay? So essentially, what we've been doing thus far all semester is specifically heterolytic bond cleavage reactions that produce ions. We've been looking at these ionic reactions and these ionic mechanisms, okay? All right, so now that's what we've been doing. That's what we've been covering. Now, radical reactions in this entire chapter is instead going to deal with what is called homolytic bond cleavage reactions, okay? So in a homolytic bond cleavage, we're going to have a bond. Again, it's going to be between things like an X and a Y. And instead of that bond being split unevenly between the two X and Y, that bond is going to be split completely evenly, right? So there are two electrons in it. In a homolytic bond cleavage reaction, one of the atoms is going to get one of the electron, and the other of the atoms is going to get the other electron. Okay, so again, there's going to be a cleavage of that bond in a completely even fashion. The product of that reaction, that homolytic bond cleavage reaction, is a radical species, right? So now we have given one electron to X, one electron to Y. They have unpaired electrons, so these are our radicals that we're going to be dealing with, okay? So now in this homolytic bond cleavage reaction, instead of using our double-headed arrow, which we use for heterolytic, instead we're going to be utilizing this single-headed arrow, all right? So in our radical reactions and these homolytic bond cleavage reactions, we're going to say that one electron goes here, and we represent that with just a single head on our arrow. And then the other electron is going to go to the other guy. And again, we represent that movement of one electron with just a single head on the arrow, okay? So these guys, because they have only a single-headed arrow, these tend to be called fish hooks because they look like fish hooks if you've ever gone fishing. And again, they're just supposed to be representing the motion of one electron, okay? Okay, so now let's talk a little bit about radicals in terms of carbon-based radical species, okay? Okay, so let's say that we had a carbon-based radical species. So let's say we had a carbon that had 3 bonds to it, right? So we had 3 bonds. Let's say that one of those bonds was split, right, in a homolytic fashion. So let's say that we have hydrogen taking one electron, carbon taking the other. The result of that homolytic bond cleavage reaction is going to be a carbon-based radical, okay? So we're going to talk about what this guy looks like, kind of relative to what other things that we have already looked at look like via structure, okay? Okay, so again, we're talking about the overall structure of these carbon-based radicals. Now, if we compare this to stuff that we've already looked at, right, this carbon-based radical, number one, it's not charged, right? So with radicals, there is no formal charge. People tend to look at radicals and say, oh, there must be formal charge, but there is no formal charge. You can calculate it for right now if you wanted to, right? If you're actually calculating formal charge here, it has a 0 net formal charge. This guy, we can imagine kind of being in between two different species that we've already seen, right? So if we take away one more electron from that, we would be left with something that we are familiar with thus far, right? Which is carbon with only 3 bonds and no unpaired electrons, no extra electrons. So we know that this guy is our carbocation. So that's kind of like, oh, if we take one more electron away from our carbon-based radical, right? So we'll put our carbon-based radical here. So one more electron, we'd get our carbocation. If we gave one more electron to our carbon radical, instead we would be left with something different. Again, we have 3 bonds to carbon, but now we would have 2 electrons, a lone pair of electrons together. So that would give carbon a formal charge here, but it would be negative. So this is our carb anion. Okay, so we can imagine that our carbon-based radical species falls somewhere between a carbanion, which is another electron added to it, or a carbocation, which is another electron removed, okay? Okay, so we know something already about these carbocations, these carbo or carbanions. So carbocation, if we're talking in terms of structure, of molecular geometry, carbocations are trigonal planar. So this guy is trigonal planar. If it's trigonal planar, it's got nice 180 bond angles, right? All of these bonds line the same plane, and it has an empty p orbital that sticks above and below that plane, so we know it's sp2 hybridized. Okay, so that is our carbocation. Carboanions or carbanions, on the other hand, in terms of molecular geometry, they aren't trigonal planar. So if you counted up all the electron groups around carbon, you would get 4, right? One of them is bonding, or 3 of them are bonding. One of them is non-bonding. So this gives us a trigonal pyramidal molecular geometry, right? And again, because this comes from a steric number or a number of electron groups of 4, this is an sp3 hybridized species, right? So carbanion is trigonal pyramidal, right? We've got a triangular pyramid, very much like ammonia when we drew ammonia back in the day. So it's essentially the exact same structure as ammonia, except with carbon in the center. And then with the carbanion, we again get that trigonal planar species, which has that empty p orbital, okay? So now, we can imagine, if we have like these 2 ends of the spectrum, the carbocation, the carbanion, that the carbon-based radical would kind of be somewhere in between, right? So it would be, instead of trigonal planar, maybe like slightly trigonal pyramidal, but we really find with respect to this guy is that it actually resembles a carbocation much more than it does a carbanion. So we imagine these carbon-based radicals being trigonal planar. We imagine them being sp2 hybridized. I shouldn't say imagine. They are trigonal planar for the most part. They're sp2 hybridized. Dyes. And the only reason why I say we imagine them is because there is a slight bend to it. There's a slight pyramid, but for the most part, it is trigonal planar. So we just say it behaves like a trigonal planar species, sp2 hybridized, okay? Okay, so the big takeaway from this, radicals, these carbon-based radicals, we're going to say they're trigonal planar, they're sp2 hybridized, they have this nice empty p orbital that's ready to make bonds. Okay, so when we're talking about these carbon-based radicals, we can also talk about their relative stability, right? And again, we've talked about very similar topics thus far with respect to carbocations, right? So for example, if I had a carbocation, and I don't know why I can't draw bonds correctly anymore. So let's say I had a carbocation and my carbon was completely surrounded by hydrogens, right? So we know that if we look at this is what we would call a methyl carbocation, right? If instead we took one of those hydrogens and replaced it with an alkyl group, right? So some other carbon chain, we know that instead of dealing with a methyl carbocation, instead we're dealing with a primary carbocation, so on and so forth, right? So we know when we, continue on, if we have our secondary carbocation, if we have our tertiary carbocation, where all of these guys are alkyl groups, we know that our tertiary carbocation is much greater in terms of stability than our secondary, and our secondary is more stable than our primary, and our primary is more stable than our methyl, right? So we know something about carbocation stability in terms of the number of alkyl groups. Essentially, the greater you increase that, the greater you're going to increase the overall stability, right? And we had explained that away in terms of something called hyperconjugation. And that was this idea that the bonding molecular orbitals from these alkyl groups were essentially donating electron density into that empty p orbital, right? And again, that orbital overlap of that, or that spreading out, that delocalization of electron density is always a nice stabilizing thing, right? So the fact that if you had more and more of those alkyl groups, you'd have more and more of this spreading out of electron density, the more stable the overall species was going to be, okay? So now we can take that and we can apply it instead of carbocations to carbon radicals, right? And we find the exact same thing for the exact same reason. So again, these carbon radicals, we're going to imagine them being sp2 hybridized with this empty p orbital hanging out, ready to make ready to make bonds or do whatever we're going to do with it, right? So because of that, because of hyperconjugation, we're going to find that methyl carbon radicals are less stable than primary carbon radicals, are less stable than tertiary or secondary, right? So again, as we increase the number of alkyl chains or alkyl groups to our carbon-based radicals, we're going to increase stability overall. Stability, right? Okay, so one way that we know or kind of one way that we measure the stability with respect to these carbon radicals is we measure something called bond dissociation energies, right? So bond dissociation energies is abbreviated very frequently via this BDE. This is defined as the energy required to break the bond homolytically in a homolytic fashion. Right, so what we do essentially is we'll take a molecule, right? Let's say that we have this methane group, right? We go in and we homolytically break that carbon-hydrogen bond, right? So we go in, we break this carbon-hydrogen bond homolytically. In the process, we generate our methyl radical, right? So we'll get our nice hydrogen, carbon, and we measure the overall energy required to make that process happen, right? So for that carbon hydrogen in a methyl group, that energy required to break that bond is 435 kilojoules per mole. And again, it's that energy that's required to produce this overall radical-based process, right? We can compare that with, let's say, this molecule over here, where we have carbon, carbon, carbon. We've got a 2-methylpropane here. So this guy is 2-methylpropane. So we can go in, right? We could look at this carbon-hydrogen bond again, same exact bond. We can break that bond homolytically, right? And in the process, instead of creating a methyl-based radical, this would be creating a tertiary-based radical, because again, that radical in the center would be surrounded by 3 other carbon chains, right? So again, we can do that. We can measure the energy required to break that bond homolytically, and what we find for this 2-methylpropane is that energy is only 381 kilojoules per mole, right? So overall, less energy is required to break that same bond because the product that we're forming is more stable. So again, this is how we know that tertiary radicals are more stable than secondary, than primary, etc., is because the bond dissociation energy is giving us an idea of the stability of the product we're forming, right? This is the easiest, we should say this is the easiest bond to break. It requires less energy because our product overall is more stable. And we're going to utilize this idea behind bond dissociation energies, and then like the weakness of a bond or the strength of a bond, for a couple more like topics. So we're going to come back to this. Okay. Again, though, overall, the larger the bond dissociation energy, that tells you that the bond there is stronger, right? Because it requires more energy to break it. But it also tells you about the stability of the product. So if the bond is stronger, then the product is less stable, because it's going to require more energy to form it, whereas the lower the bond dissociation energy, the weaker the bond overall, but the more stable the product. Okay, so just be aware of that trend where methyl is a higher bond dissociation energy than a primary, than a secondary, tertiary, and that deals with the stability of the overall radical product. Okay, so again, with respect to things that we have already dealt with versus things that we're going to learn this chapter, we learned a lot with respect to ionic-based reactions and ionic-based mechanism. We also learned a lot with respect to ionic-based resonance structures. So if you guys think back way at the beginning of the course, we learned a couple of different patterns with respect to drawing resonance structures in an ionic-based mechanism, right? So for example, let's say we had a positive charge that was in an allylic position to a pi bond, right? So we would have called this something like the allylic positive charge, or allylic carbocation positive charge. And we know that there's a pattern that we can draw a resonance structure for this guy, right? If we have a pi bond and we have a positive charge in an allylic position, those electrons of that pi bond can go, they can fill that hole. And another way that we can draw this, or another resonance structure of this, is this guy, okay? So again, that was a pattern that we learned for heterolytic bonds, for ionic-based mechanisms, okay? We're going to learn a very similar type of pattern for our radicals, but just note that we're actually only going to learn one pattern for radical-based resonance, as opposed to the like 4 or 5 patterns that we learned for our double-headed arrows for our ionic-based resonance structures, okay? All right, so the only pattern in terms of resonance structures that we can draw for radicals that we're going to learn is a radical in the allylic position. So we can call this an allylic radical, okay? Okay, so the pattern that we're going to learn is going to involve 3 fish hooks. So overall, we're going to get 3 fish hook arrows. And the way it's going to start is we're going to start at the radical. All right, so we have our radical here. What's going to happen is this guy's going to go. It's going to form 1/2 of a bond. All right, so we're going to show the movement of that guy via this fish hook. We're going to come to this pi bond, and we're going to take one of those electrons in that pi bond, and we're going to create the other half of that bond. The other electron is instead going to stay on that outer carbon, right? So what we're going to get as a resonance structure for this is we essentially have, let's see, let me get my highlighter. We have this guy and this guy making a new pi bond. That's going to break that old pi bond, but then at the very end, that extra electron that goes out here is going to essentially move out here to create our new radical, okay? So again, if we drew that again, or if we do that in a little bit more complex of a problem, let's say that we had this guy in our radical here. To draw a resonance structure for this radical, because we know that it is an allylic radical, right? Because again, we have we have a double bond, and we have a radical in the allylic position to that double bond. We're going to start at the radical. We're going to use it to form one half of a bond. We're going to use one of the electrons in that pi bond to form the other half, and then that other electron is going to stay on the carbon that terminates that double bond. Right? So at the end of this guy, we will get a double bond here, and we would get a radical on this carbon. Okay, so that's kind of the basic pattern that we're going to learn in drawing resonance structures for radicals. Another kind of like caveat or spin-off of that is not only will we find that for an allylic structure or an allylic radical, but also for a benzylic radical, right? So this is going to be a radical where you have an aromatic ring, right? So we have an aromatic ring. The benzylic position is defined as this bond or this carbon that's adjacent to the aromatic ring. So what we find if we have this benzylic radical is we'll find the same thing. We'll have our radical making one half of the bond, the double bond as part of the aromatic ring, form the other half, and then this other electron going up here. Now, though, with respect to this benzylic radical, we can draw multiple resonance structures for it, right? So now, again, we've got our radical. It's in an allylic position, so we can do the same thing where we have fishhook arrow for one of our electrons, fishhook arrow for the other, fishhook arrow for the other. The product for this guy would be something that looked like this, where we have a double bond, we have our double bond here, we have our double bond here, and now we have our radical out here. Again, there's more resonance that we can draw for this. So we can take this guy, we can make one half of that bond, we can take this guy, make the other half of this is going to stay with this carbon, and so we would be left with, at that point in time, something that looked like this. So double bond here, we've got a double bond here. We've now moved the double bond here. We've got our radical here. And then finally, we can do one more of these guys where we take this guy, make a bond here or half the bond here. This guy is going to make the other half. This guy is going to move up here. And we are left finally with where we started at, which looks something like this guy. Okay, so again, it's a similar pattern. It's just now you get multiple of them because, again, you get multiple different allylic radicals that can essentially delocalize around the ring, okay? Now, that's the pattern for benzylic radicals. Note how many different resonance structures we could draw for that. So overall, we had 1, 2, 3, 4, and then that end one just got us back. If we compared that to our allylic radical up here, we only had 1, 2 different resonance structures, right? And just as a reminder, the more the overall resonance structure, so more resonance structures, what does that tell us about the overall stability of the molecule? So the more resonance structures, the more stable the molecule, okay? So because of that, benzylic radicals are the most stable of all of the radicals, most stable. So again, in terms of that bond dissociation energy, the carbon-hydrogen homolytic bond or homolytic bond cleavage reaction that produces that benzylic radical is going to have the lowest bond dissociation energy, lowest BDE. Okay, so benzylic radicals are the most stable. Again, they have lots and lots and lots of resonance structures. If we had gone back up to this guy, our allylic radical, note that if we were classifying this based on primary, secondary, tertiary, etc., this guy here, no, I highlighter. This guy here, we would say, oh, well, that is a primary radical, right? And so you'd be like, oh, primary radical, probably things like tertiary radicals are going to be more stable than it, but that is actually not the case. Even though this is a primary radical, because it is allylic, it is actually going to be more stable. So more stable than a tertiary radical. So overall, in terms of stability, what we find is we get methyl radicals, we get primary, we get secondary, we get tertiary, we get allylic, and then we get benzylic. And then one last thing with respect to this, so we've talked about allylic and benzylic. We have not talked about the vinyl position, right? So just as a reminder, there's two different positions with respect to the double bond. If we're here, this is the allylic position. It's the carbon directly adjacent to the double bond. If we instead were here at this carbon, this is the vinylic position or the vinyl position. So vinyl or vinylic, all right? Now, if we drew on the implied hydrogen here, if we had underwent some sort of homolytic bond cleavage reaction between this carbon and this hydrogen, we would generate as a product here something called the vinylic radical. Okay, so this is a vinylic radical. This is actually the least stable of all. So this is the least stable, even less stable than methyl radicals, right? So if we were going to add this, then vinylic would be down here. So don't get the vinylic and the allylic positions confused. Vinylic radicals are super unstable. They're even less stable than methyl, whereas allylic, again, which would be a radical at the allylic position, are much more stable comparatively, more stable even than a tertiary radical. And again, comparing that to a benzylic is the most stable. Okay, so how are you guys going to utilize this information when we're talking about these stabilities with respect to these bond dissociation energies, okay? So one type of problem that you're going to see is you're going to be given a molecule and you're going to be asked, hey, can you tell me who is the weakest carbon-hydrogen bond here, right? This goes back to this idea that we've been talking about how bond dissociation energies are going to be intimately associated with the types of radicals that they're going to produce. And the more stable the radical that you're producing, the lower overall the bond dissociation energy, the weaker the bond, okay? So for example, let's say that we were saying, okay, got this molecule and I'm trying to identify the weakest carbon-hydrogen bond. What I'm trying to identify here, if it's the weakest carbon-hydrogen bond, then I want the smallest bond dissociation energy, right? Because the lower the bond dissociation energy, the less energy is required to break it, the weaker it is overall. And what that means in terms of the radicals produced is I'm looking for the thing that's going to produce the most stable radical. All right, so I'm going to start off at kind of like a low ball one, right? We'll start off on the outside here. I've got these carbons, and these carbons, if I go ahead and just draw them in here, all have bonds to 3 hydrogens, okay? So let's imagine that we looked at the bond association energy for one of these carbons, right? And again, in these bond association energies, we're cleaving these bonds homolytically, right? And so we could do that, and as a product, we would generate a radical at this position, okay? So we can draw everything else in, and we can kind of assess the type of radical that we formed by breaking one of these carbon-hydrogen bonds in this homolytic fashion, right? So if I look at this, I say, oh, well, in this process, what type of carbon radical am I forming? This specifically is a primary carbon radical, right? It is only bound to one other alkyl chain. The rest of those bonds are to hydrogen, so this is a primary carbon radical. Okay, so I could do the same thing for other bonds. So if I did the same thing out here for these guys, these again are all bound to hydrogen. I get the exact same primary radical up here. So these would both be primary radicals. If instead I looked here, I have a carbon-hydrogen bond here, and I want to know kind of something about the product of that bond cleavage reaction. Again, this is a homolytic bond cleavage reaction. Overall, I would get something that looked like this, where I get a radical here. All right, so again, if I split that bond, that carbon-hydrogen bond, in a homolytic fashion, I'm looking at that as its bond dissociation energy. The product overall is going to give me a tertiary radical at this point in time, okay? So we can do that for other carbon-hydrogen bonds, right? So if we move on and we look at this guy, we'll find, oh, well, at this position, there are no carbon-hydrogen bonds, so we can ignore that. If we move on to these guys, it would be the same thing as this guy out here, right? It would just give me a bunch of primary radicals. If I moved on to this guy, right, we've got a carbon here. Oops, we've got a carbon here. We can imagine it's attached to two hydrogens, so we can take one of those carbon hydrogens. The product overall here would give us something that looked like this, where we get our carbon radical here. We've got this guy, and a double bond, right? And at first you would say, oh, well, this is just a secondary carbocation, right? And so you're like, okay, well, if that's it, we keep moving out, then tertiary is more stable than secondary. But you're also ignoring the fact that this is actually an allylic carbocation as well. All right, so not only do we have this structure, but we can draw a resonance structure for this, where we have the double bond moving to that position, and as a result of this, we would get something that looks like this, where we get a double bond here, the radical goes out here, we've got this guy and this guy. So because this is an allylic carbocation, at this point in time, carbocation, this is the most stable, even though we do have a tertiary carbocation over here. And so right now it's going to be winning in terms of being the most stable radical. And so as a result of that bond cleavage having the lowest bond cleavage, the smallest bond cleavage, or bond dissociation energy being the weakest carbon-hydrogen bond. So again, we can keep coming out here. Here we have a hydrogen. Here we have two hydrogens. Again, though, if we had cleaved any of these guys, so let's say that we cleaved this one, this guy left here, we drew the product, let's say down here, we would end up with a radical that instead of being in the allylic position is in the vinylic radical. And so we know that that is bad in terms of stability. So this is going to be the least stable of all of the ones that we have drawn at this point in time. So likely these carbon-hydrogen bonds on this double bond, these guys would probably be actually the largest bond dissociation energy. And so again, that would probably give us overall the strongest bond, the strongest carbon-hydrogen bond. We're not looking for that, though. Again, we're looking for the weakest carbon-hydrogen bond. So we've kind of analyzed all of the carbon-hydrogen bonds. At this point in time, we can go back and say, okay, the thing that generated the secondary allylic carbocation is going to be the weakest. It's going to have the lowest bond dissociation energy because, again, the radical that it produces is the most stable. So the answer to this question would be the identification that this bond, or this bond, whichever one you wanted to say, that's going to be the weakest carbon-hydrogen bond in the compound. Okay, so hopefully that made sense somewhat. All right, so go ahead and try this one on your own. So I give you a structure, and again, it's the same thing. I want you to identify the weakest carbon-hydrogen bond in the following molecule. So pause this, give us a chance, and then come back for the answer. Okay, so let's go ahead and we'll talk about this one. So we're going to start, and kind of, again, there's kind of softball ones on the outside. So let's imagine the type of radical we would form if we cleaved in a homolytic fashion the carbon-hydrogen bonds on this outer carbon, right? So if we did that, again, homolytically, we would be left overall with the production of something that looked like this, right? Where we would generate that radical on that outer carbon. Again, in that process, we would be generating a primary radical, which we know is not super stable, okay? Now, if we moved inside instead, let's say we were looking at this carbon-hydrogen bond, right? So we know there's a carbon here. There is one hydrogen left. We're looking at the weak, or the bond association energy for this guy. I don't really like that. So we'll have our carbon, we'll have our hydrogen. Again, we're going to be cleaving that in a homolytic fashion. The overall product for this guy would be something that looked like this, right? Which would give us a radical here. And note again that that radical is in an allylic position, right? So it's in an allylic position for two different pi bonds. So we have a pi bond here, a pi bond here. So we could draw resonance structures for both of those. That would give us 3 overall resonance structures. But again, just note that this is an allylic carbon radical. I hope I haven't been saying carbocation, have I? Nope, I'm writing it now. Okay. So again, allylic carbon radical. Okay. All right. So the only other types of things that we can look at are, again, these guys where we have this carbon hydrogen, right? If we cleaved that bond, we already know that we would be generating, again, something that looked like this, where we'd get a radical right on that carbon-carbon double bond. Again, this would be a vinylic, so this would be a vinyl carbon radical, which is bad. And then finally, if we look on the outside here at this guy, so again, we get the same thing. If we did that, if we did this, if we did this, we get a vinyl radical, which is not stable. It's the least stable. Least stable. So that would have the, it's the strongest bond. So the highest BDE. BDE. And so then finally, we have these guys out here. So we do have 2 hydrogens out here. If we cleaved one of those, oh no, I ran out of things to copy. I'm going to copy this guy because I refuse to redraw this. So if we're out here, let me just erase this guy. Erase this guy. When we take one of these guys, the thing that we're going to be left with is another allylic radical. So this is another allylic radical. So you may say, okay, well, how do I know? We've got this allylic radical versus this allylic radical. So now that whole secondary, tertiary, primary thing does come into play. This is a secondary allylic radical, whereas this guy was a tertiary allylic radical, okay? So because tertiary is more stable than secondary, the tertiary allylic radical is the most stable. So as a result of that, the bond association energy here is the lowest. So this carbon-hydrogen bond specifically is the weakest bond, weakest carbon-hydrogen bond, right? So if you were going to identify that in your answer, you would say that this guy is the weakest. So hopefully that makes sense. So as we get into drawing out these radical-based mechanisms, so we just learned how to draw the arrow pushing pattern for drawing resonance structures with respect to radicals. So now we're going to move into kind of learning our patterns with respect to radical-based mechanisms, so the steps that are going to be involved. And again, this is going to be very similar to stuff that we've learned in terms of our ionic reactions, right? So when we talk about reaction mechanisms and our steps or our pattern or arrow pushing patterns. So we know that in ionic reactions, we have a couple of different patterns. Right? One of those was, let's say, a nucleophilic attack. Right? So we had learned that pattern of nucleophilic attack. We had another one, which was loss of leaving group, right? So we had learned that pattern with respect to arrow pushing for a leaving group leaving. Same thing with, let's say, proton transfer, right? We learned that pattern with the arrow pushing. And then our last ionic reaction base arrow pushing pattern was carbocation. So carbocation rearrangement. Right, so these are the four basic patterns that we learned for our ionic reactions. We're going to do a very similar thing where we learn patterns for our radical-based reactions. But except the big thing to note here is that these guys and our radical-based reactions are not going to be the same, like at all, right? So let's say that we had a structure, for example, where we had some sort of primary radical, right? If this was a primary carbocation, we would see carbocation rearrangement, right? Because, again, this could rearrange via a hydride transfer into a tertiary carbocation, which would make it more stable. If we saw the same thing for radical, we're not going to actually see radicals rearrange. So these mechanistic steps that we've learned for ionic reactions are not going to be applicable at all to radical reactions, okay? So then, well, what are these patterns that we're going to learn? So unfortunately, there are 6 of them, and I'm going to go through the steps for all 6, but at the end of the day, a couple of them are essentially just the reverse of the other, so it's not going to be super hard to learn these, and we're not going to actually use them that much, so it's mainly just the couple of reactions that we're going to deal with in this chapter, okay? All right, so the first one that we're going to learn is what is called homolytic cleavage. So in homolytic cleavage, we're going to have a bond or a molecule, right? It's going to have a bond, and we've already talked about this. In homolytic cleavage, energy is going to be supplied to homolytically cleave this bond. And so for this guy, this bond, we have one Fishhook arrow going to one atom, the other Fishhook arrow going to the other. And the product of this reaction is going to be the generation of these 2 radical-based species, okay? So it is important to note that energy is required for this. We have to break this bond. You always need energy to break this bond. So energy is required in this step. And that energy that we'll talk about later is usually either supplied in the form of heat. So this is heat, or it's supplied in the form of light. And we represent light here as H nu. And again, let me just write that so no one gets confused. H and then nu is what I'm saying. Okay, so that's the first one, homolytic cleavage. Again, we take something that is not radical-based, we cleave that bond homolytically, and we produce 2 radicals as a process, as a product, okay? All right, so the second one is something called addition to a pi bond. So in this guy, what we're going to have is a pi bond. We're going to have a radical come along, and what it's going to form is essentially it's going to add to this molecule, right? So we're going to have our radical form one half of our new bond. The pi bond is going to form the other half between this X and this carbon, and then the other part of this pi bond is going to be left on this carbon. Okay, so the product of this is going to be an X to a carbon to a single bond to a radical. Okay, so again, this is addition to a pi bond. Note that it uses 3 arrows, 3 fish hooks, and we enter with a radical, and we leave with another radical. So a radical generates another radical. This guy only used 2 arrows up here. All right, so then the third one is something called hydrogen abstraction. So again, we're going to have a radical come along. We're going to have a molecule that has a carbon or an alkyl to hydrogen bond. This radical is again going to form half of this new bond that's going to form between H and X. The other half is going to come from this bond, and then the remainder of this bond is going to be left behind on the alkyl group. So we're going to end up with a a new X bond to H, and then we're going to end up with a alkyl base radical here. Okay, so then in another step, this is called halogen abstraction. What's going to happen is we're going to have a radical, usually an alkyl radical, come along. It's going to react with a halogen, and it's going to do essentially this exact same thing that we saw for hydrogen abstraction, where this guy's going to come along. It's going to form a bond with a halogen now. Again, one of the electrons is going to come from the radical. The other is going to come from that bond between the dihalide. The other electron is going to be left behind, and we're going to get a new alkyl halogen bond, plus we're again going to generate another halogen base radical. So this guy used 3, this guy used 3. Again, we entered with the radical, we left with the radical, we entered with the radical, we left with the radical. Finally, elimination, or not finally, there's 2 more. So in an elimination-based reaction, we'll have a radical-based species. We'll call the carbon that the radical is on, we'll call this the alpha carbon. We will then call this guy the adjacent one. This guy is the beta carbon. What's going to happen here is a bond is going to form, or a pi bond specifically, is going to form between the alpha and the beta. Right? So one of the electrons is going to come from the radical. The other is going to come from this bond. And at the process, at the same time, this bond's going to get cleaved homolytically, and it's going to kick off that halogen. Right? So the process of this guy is going to give us overall our halogen-based radical and then a double bond. And then finally, coupling. So coupling, what happens is you take a radical and you combine it, and I'm going to get rid of this X or this guy. You combine it with another radical, right? So essentially, they're going to form a bond between the two, and you're essentially going to have this coupling of these radicals. You're going to bring in radicals, and at the end of the day, there are no radicals left, right? They're going to couple together, they're going to form a bond, and essentially do what we call annihilate one another. And so this guy has 2 arrows. Again, we enter with a radical, but there are no radicals at the end. This guy uses 3 arrows. We do enter with a radical, and we do have a radical still left at the end. Okay, so those are the 6, right? Again, that's a lot. It seems like a lot, and it is a lot. But just note that a few of these are just the reverse of one another, right? So for example, homolytic cleavage, right, where we have a non-base radical species, we homolytically cleave that bond to produce radicals. This is essentially just the exact reverse reaction as the coupling reaction, right? Taking those 2 radicals, putting them back together to form a non-radical species is the reverse of homolytic cleavage, okay? So homolytic cleavage is the reverse of coupling. And then if we look at addition to a pi bond and elimination, these guys are also just the reverse of one another. So elimination is the reverse of addition to a pi bond. And then at the very end here, I erroneously say hydrogen abstraction is the reverse of nothing, right? So the reverse of hydrogen abstraction would just be another hydrogen abstraction, right? That's the reverse of that, so that doesn't make sense. And it's the same thing for halogen abstraction. For both of these guys, the reverse of them is just the same exact reaction, right? So the reverse of hydrogen abstraction is hydrogen abstraction, and the reverse of halogen abstraction is halogen abstraction. Not hydrogen, but halogen. But I just wanted to repeat the abstraction word because I don't want to write it again. Okay, so those are the 6 basic patterns. Those are the 6 basic mechanistic steps that you guys are going to need to be aware of. But what's nice is that with respect to all radical-based reactions, they all follow a couple of guaranteed different steps. So what do I mean by that, right? So all radical-based reactions have the following three basic steps involved, right? They have a first step, which is called initiation. They have a second step, which we call propagation. And then they have a third step, which is called termination, okay? And so all of these radical-based mechanisms, all these reactions will be initiated, and the only pattern that can initiate a radical reaction is the creation of radicals from non-radical-based species, right? So the only thing that can do that is homolytic cleavage, right? So of our pattern, the only thing that can actually initiate a radical-based reaction is that homolytic cleavage reaction. If we look down to termination, in termination what we have is radicals coming together and annihilating one another. Again, the only step that can accomplish that in those patterns that we just learned is coupling. Okay, so then if all radicals are initiated via homolytic cleavage, if they're all terminated via coupling, then in the middle we propagate, right? And propagation can be any of those four that were in the middle, right? So addition to a pi bond, hydrogen abstraction, halogen abstraction, elimination. For all of these guys, for this propagation step, we're always going to need to be coming in with a radical as our reactant, and we need to be propagating more radicals or creation of more radicals as a product, right? So any of those steps that had a radical come in and had a radical leave, they can fulfill this propagation step depending on the overall mechanism that we actually see. Okay, so again, which we actually use between addition to a pi bond, hydrogen, halogen abstraction, or elimination, this depends on the reaction. Depends on reaction. But initiation will always be homolytic cleavage, termination will always be coupling, and then these propagation steps is going to depend on what reaction we're actually looking at. Okay, so with that in mind, now that we have the patterns for these radical-based mechanisms, we're actually going to go through the mechanism for our first reaction, which is specifically the chlorination of methane. Okay, so in this reaction, our overall reaction, what we're going to find, we're going to take methane, we're going to react it with chlorine in the presence of light, and the product overall we're going to get is our methyl chloride. Okay, now, a couple things to note here with respect to this mechanism, right? So this is going to be important, and long term we're going to talk about what reaction we're really actually going to move forward with. But just as a note, right, we thus far in our pathway through organic chemistry, we have never been able to take something that is not functionalized, right? So just a plain alkane and introduce a functional group to it. Right, so if I had something like propane and I wanted to make, let's say, propanol, at this point in time, we don't have a means by which we can do that because we can't take an alkane and introduce a functional group into it yet, okay? So that's going to kind of give you an idea behind the importance of these overall reactions. This is going to be the first time where we do take an alkane, right, so something like methane, and we introduce a functional group in the presence of, or in the form of a halogen to it, right? So we take an alkane and we make an alkyl halide, okay? So functionally, this is going to be mildly important, okay? Now, again, with respect to all of these radical-based mechanisms, they're all going to have the same three basic steps where we have an initiation step, a propagation step, and a termination. The propagation is where these guys actually differ depending on the mechanism. And so in this mechanism, we're only going to see two of those propagation steps. We're only going to see hydrogen abstraction, and we're going to see halogen abstraction, okay? All right, so first off, what is our first step here in our chlorination reaction with respect to methane? So the first step, what's going to happen is that chlorine, right, is essentially going to come along, and it's going to be homolytically cleaved. And again, this is going to be in the presence of heat or light. So we're just going to write light here. That's going to provide the energy to take this bond and homolytically cleave it. As a result of that, we're going to end up with two chlorine-based radicals. Okay, so this is our initiation step. It starts with the chlorine. Okay, so now in our second stage of this mechanism, we're going to see, first off, our first step in this, we're going to see hydrogen abstraction. So this first step is going to be hydrogen abstraction. What's going to happen, abstraction. So what's going to happen is our newly formed chlorine radical is going to come along. It's going to find a methane. Right, so we can draw out our little methane. And that chlorine radical is going to abstract a hydrogen from that methane. Okay, so in that hydrogen abstraction, we've got the radical making half of the bond, the other half of the bond coming from the carbon-hydrogen bond, and then that other electron is going to be left behind on the carbon. Right, so the product of this first step is going to be H to Cl, right, and we're also going to get the production of our methyl radical here. Right, so that's step number 1. Now, in step number 2, what we're going to see is instead of hydrogen abstraction, our second step is going to be halogen abstraction. So our methyl radical, and I'm going to draw it this way, is going to come along. It's going to find another halogen. That is not an X, that is a Cl, because we have defined what it is. So we have Cl to Cl. And it's going to abstract that halogen, right? So again, we've got this radical going to form this bond. We've got the other part of the bond coming from our chlorine-chlorine bond, and then that's going to leave behind that one electron on the chlorine. So as a result of this, we get our chlorinated methane, our methyl chloride, which is the product we want, and we also get another chlorine radical, okay? So note, we entered with a chlorine radical, right? So this was a chlorine radical. We are now producing a chlorine radical at the end, okay? And so this kind of having something come in and reproduce itself at the end so that this can essentially go back to the beginning and redo this and redo this and redo this over and over. This is kind of the hallmark of something called a chain reaction. Right, so all of these radical-based reactions are chain reactions because in this propagation step, we regenerate the thing that started it at the beginning, okay? So propagation undergoes this chain reaction. Once we bring in our chlorine radical, we're going to reproduce the chlorine radical at the end, which can then come back, re-enter this, attack another methane, and continue this on and on and on. Okay, so again, it will continue that on and on and on and on until it kind of runs out of stuff to react with, and the reaction terminates. Okay, so there are a couple different ways that the reaction can terminate here. The first way, we could have a chlorine radical combine with another chlorine radical, so couple with another chlorine radical. So the result of that would give us, again, that just chlorine molecule. Another thing that could happen is a chlorine radical could couple with one of our methyl radicals. Right, so these guys could bump into one another, they could couple, and we would end up with our methyl chloride. All right, but again, for both of these, we're taking radicals in, and we're not producing radicals at the end, right? We're removing, annihilating those radicals. And then the final way that this could end is one of the methyl radicals could find another methyl radical. And again, they bump into each other, they couple with respect to one another and annihilate each other, and we would end up at the end with this with respect, or with our product of ethane. Okay, so again, initiation is homolytic cleavage. Specifically, it's homolytic cleavage of the dihalide. Okay, again, that utilizes light to do that, to provide that energy. Once we produce that dihalide, we enter into our propagation stage, where first off we see hydrogen abstraction, then we see halogen abstraction, and that undergoes that chain reaction of propagation until we start to run out of things. And at that point in time, we're going to reach our termination stage, where we can either have the chlorine radicals coupled together, we can have a chlorine radical couple with a methyl radical, or methyl radical can couple together. Again, for all of these guys, we're taking radicals in, and we're producing non-radical species at the end of this. Okay, so that is the mechanism for our first reaction, the chlorination of methane. Okay, so now there's a couple other things that I want to mention with respect to this mechanism that applies to all of these radical-based mechanisms. Okay, so the first thing to note is that, again, with respect to that propagation stage, whatever happens in that propagation stage is actually going to represent our overall reaction, okay? So just as a reminder, with respect to these mechanisms, we're always supposed to be producing some sort of guide map or roadmap on how this reaction takes place. And in terms of ionic-based mechanisms, when we take all of the steps and we sum them together, we should get the overall balanced reaction. That is not the same in radical-based mechanisms, right? But what is the same is that if we take the steps of the propagation part of the mechanism and we add those together, or we sum those together, that should give us the overall the reaction that we're actually looking at, right? And I'll try to explain what we mean by that. Again, in the chlorination reaction here, we have methane, right? Overall, it reacts with chlorine to produce our methyl chloride, so C3Cl and HCl. Okay, this is our overall reaction. Again, if we were dealing with with an ionic reaction to produce a valid mechanism, all of our steps would have to sum to this overall reaction. That's not this case in terms of this radical-based mechanism. Instead, it's all of the steps of the propagation stage that have to sum to this overall reaction. So we had two steps in the propagation phase. We had hydrogen abstraction and then halogen abstraction. When we add these two guys together, anything that shows up as a product as well as a reactant in the same form, we're going to get rid of, right? So for example, here we have a methyl radical. We also have a methyl radical here that we can cross out. Here we have a chlorine radical. We also have a chlorine radical here that we can cross out. And so when we add these guys together, we're going to end up with our methane, CH4. It's going to be added to our chlorine, our dihalogen. That's going to give us our HCl and our methyl chloride, CH3Cl. All right, so again, it's these steps of this propagation component or portion of the mechanism that are going to sum to this overall reaction that we're trying to represent. Okay, and so then finally, with respect to this chlorination reaction, what we find is that if we use a large excess of chlorine, so if we were to use lots and lots and lots of chlorine, we would not just get our nice little monochlorinated product of methyl chloride. Instead, this methyl chloride is even more reactive to this chlorination mechanism than methane was. So if there was a large excess of chlorine, then it would also undergo chlorination to the methylene chloride, to the chloroform, and then all the way to the fully halogenated product of the carbon tetrachloride, okay? Many times we do not want this or this or this. Many times we only want this, right? And so mechanistically or experimentally, to prevent this polychlorination, what we do is we use a large excess. So a large excess of methane and very limited amount of chlorine. So limited chlorine, so that we do end up with just the methyl chloride, with just the monochlorinated product. Okay, so I think I'm going to stop there for today because I think we're about to enter into oh, no, actually, no, let's not do that. I can talk for a little bit longer, okay? So, yeah, take away whatever I've said already on this slide. Take that away, learn something from it, okay? All right, so now in this last little bit for today, at least, what I'm going to talk about is something called radical initiators, okay? So we've already mentioned that the initiation step or the homolytic cleavage step requires energy. Specifically, it requires quite a bit of energy, and that can come in the form of heat, right, which is what we represent as our delta, or this could also come in the form of light, okay? Now, if we are using light, it has to be of high enough energy to, again, homolytically break this dichlorine bond. And so we'll find that light in the UV region of the electromagnetic spectrum will actually give us enough energy. If instead we were using heat, we would actually have to heat up the reaction to a couple 100 degrees Celsius to provide I think they said specifically hundreds, let's say hundreds degrees Celsius, to actually provide enough energy for this to go, okay? So a lot of times we don't want to do that. If we start to heat things too much, we'll get unwanted byproducts, etc. So one thing that we can do is utilize something called a radical initiator. And the idea behind this is going to be a species or a molecule that has a very easily cleavable bond, right? So it requires less energy to actually undergo that homolytic cleavage. And then once that radical is produced, it can then move on into the propagation to actually continue to propagate the production of more radicals, okay? So one of the big ones that we use, you guys may be familiar with, are these peroxide-based species. So peroxide, just a general peroxide, has this nice kind of easily breakable oxygen-oxygen peroxide bond. So to homolytically cleave this, the bond dissociation energy is only 159 kilojoules per mole, which is about 100 kilojoules per mole less than that chlorine-chlorine bond. And again, it's just because this oxygen radical is fairly stable and it's fairly easy to make. Another very common one that we'll utilize is something called an acyl peroxide, right? So this guy, again, has this nice bond that is fairly weak and easily cleavable. So this bond only requires 121 kilojoules per mole. Again, we'll get the radical as our product, or we'll get two of them. The reason why this one doesn't require as much energy comparatively to just the peroxide-based species is because, again, this guy can be stabilized via resonance. So stabilized via resonance. And again, because of that, this is more stable than just the peroxide-based product over here. And so it's going to have a smaller bond association energy. Okay. So again, the purpose of these guys, we'll throw them in to initiate our radical-based reaction. And all they're doing is essentially creating radicals at a lower bond association energy that can then go on and react with our halogens or whatever else we have in there to propagate and move the reaction along. Okay, so that is actually, I think, all I'm going to say for today, because we're about to move into talking about some thermodynamic things with respect to all of the halogens. So we've talked about specifically about chlorine, but as we move into the next few slides, we'll talk about other halogens like bromine, fluorine, iodine, whether or not we can do this reaction with them, and then what's going to be kind of like the products or the various products that we can get out of it. So email me if you guys have problems, if you have any issues. I'll hopefully have the homework up for chapter 10 here in the next day. And I hopefully you guys are keeping up with the PowerPoints and they're not super boring, though they probably are. So hope everyone is doing well. Bye.